Hello, and welcome to this special event that is part of the Cosmos Prize initiative. For those among you who join us for the first time, let me just say a few words about the prize. The prize is organized in synergy with the Ministry of Education in Italy and the Planetarium in the city of Reggio Calabria in the south of Italy, the Italian Astronomical Society, and the two cultural foundations, Fondazione Con il Sud and Reggio Emilia. The goal of the initiative and the mission of our initiative is Science for All. And this has two meanings. It means promoting outstanding science outreach by celebrating authors who make science accessible for a large audience and engaging all young people with science, including young people with disadvantaged socioeconomic backgrounds. And aligned with these two meaning, with these two goals of this initiative, we organize every year, we assign two prizes. One is assigned by a scientific committee of scientists active in popular science. And this is what the so-called Cosmos Prize. And there is a separate prize, which is awarded by high school students, hundreds of high school students who participate in the initiative and awarded independently their own prize. Today is a very special event. I'm actually very happy. I'm delighted to have here with us today Brian Greene. Good morning, Brian.
Hi, good to see you.
Brian is a professor of physics and mathematics at Columbia University and the director of Columbia's Center for Theoretical Physics. He's known to the public through his best-selling books, numerous media appearances, and he's also the co-founder of the World Science Festival. His most recent book, Until the End of Time, has been shortlisted for the Cosmos Prize Award. Also here with us today is the Cosmos Prize jury member, Carlo Rovelli. Good morning, Carlo.
Hi, pleasure to be here.
Carlo is a professor at the Department of Physics at the Aix-Marseille University. He's an adjunct professor at the Department of Philosophy at the University of Western Ontario and a distinguished visiting research chair at the Perimeter Institute in Ontario, Canada. Thanks a lot, Brian and Carlo, for joining us today. You're both very well known, both to fellow scientists for your groundbreaking scientific contributions and to the general public for your extraordinary work and outstanding contributions to the public understanding of science. Instead of doing like a strict Q&A session with shortlisted author Brian Greene, Carlo and I thought that we could take this unique opportunity of having the two of you here today and to really have a conversation that we start from your book, Brian, and we'll eventually touch on topics that I hope, like the origin and the end of time, as the title of the book says, entropy, string theory versus loop quantum gravity. You're proponents of this and founders of these two different approaches to really the most fundamental theory of nature, a quantum theory of gravity. And maybe even beyond. Maybe you can share your experiences as rock stars of physics and best-selling authors. So, Brian, perhaps we can, perhaps a good starting point for our conversation could be really the beginning of your book. And the first sentence of chapter 1 of your book, you write, "In the fullness of time, all that lives will die," which is a pretty dramatic way of starting a book and definitely an effective way of capturing the attention of the reader. Now, you later mentioned that this thought touched you viscerally and that never before physics and mathematics had overwhelmed you with a hollow dread. Now, to reassure our viewers, in the rest of the book, you tell us how you eventually turned this very deep emotion into a very different feeling of calm, of connection, even gratitude. But before we discuss all that, could you maybe start by elaborating a bit more on this very powerful feeling evoked by pondering the end of time and why it was so powerful, almost traumatic for you, one could even say.
Yeah, absolutely. I'd be happy to. Many of us physicists, we are excited to do what we do to reveal some secrets of the cosmos, some fundamental quality or pattern out there in the world that hasn't yet been found, that we can find equations to describe. I mean, that's sort of the lifeblood of what we do. But all too often, I certainly find that with some of my students and some of my colleagues, and Carlo can speak to his experiences as well, which I suspect are not that dissimilar, we can get so focused on the details of what we're doing that we can lose sight of the bigger picture of how we as human beings fit in to this grand cosmological unfolding. And when we realize, as I certainly did, as I described in that opening sentence, when we realize our own mortality, when we fully take in that our lives are finite, we can find that realization to be profoundly formative in what we find to be important. And I certainly encountered that as a young student in two particular books, one by Oswald Spengler that I described called Decline of the West, another book called The Denial of Death by Ernest Becker, won the Pulitzer Prize in the 70s for that book. And both these authors in their own way argued that the singular realization of human beings that we are mortal, there really isn't any other species that walks around with that knowledge inside of their heads, but that singular realization can be viewed as something that has driven much of human history. And when I began to think about things in that term as a younger student, it had a profound impact on me. When you recognize that everything we care about is going to go away, every element of our lives that we stitch into a larger pattern of meaning and purpose will all disintegrate in the fullness of time. Yes, if you take that in fully, it really can give you a different outlook on the world. And as you rightly described, ultimately, and perhaps this will be part of our unfolding conversation here, I took in that knowledge and came to a place of acceptance, which ultimately I think has given me a deeper appreciation for existence at all. And that's a journey that someone can go on. I think it's a valid and vital one to do.
Great. So let me bring in Carlo at this point. Carlo, what was your reaction when you read about this hollow dread? Is that something that resonates with you?
Yeah, thank you, Gianfranco, for this question, for this very good opening, going in a sense to core of matter, and thank you for having given me this opportunity of this conversation with Brian, which is an opportunity, in fact, to read his book with attention, which I very much have welcomed and has an effect on me. Let me put it this way. I find some extraordinarily deep similarities between my own path and Brian one, and some remarkable differences. And I guess I want to say something about that and see how Brian react to that. For those who are listening, of course, I know Brian's work. I know obviously his popular works, his presence in books, media, and so on. A fantastic work he has done. But we have crossed one another only occasionally, very little, and we have directly spent only a few words between us. Not much. So we are not close friends or collaborators. And let me put it this way: I have been amazed by how good he is in doing things. There's no doubt. I remember one among the many, one absolutely spectacular appearance of him on TV with a little laser and him shouting and showing how the waves of the sun make the interference in the interferometers move, and giving the most simple and spectacular presentation of how LIGO works for the gravitational waves. I think is a genius in the capacity of explaining modern physics. I admire him enormously, but at the same time, I always felt a distance from Brian. Let me put it this way: we're different. We're different in a number of ways, and to my ear, there was something cold and distant in his way of presenting things, like he's not really engaged. And I recognize this. I think there is some deep difference. I recognize precisely in the opening of his book, when he says that he was attracted by mathematics and physics at the beginning. What really captured him and took them him was the fact that, as he says, theorems are true forever. There was something fixed, eternal, secure, sure, sort of out of time in the knowledge that mathematics could afford. I was attracted by science by the opposite, by the fact that you go into science and you discover what you find you thought was true is false in some sense. It's imprecise, it's missing, it's because it challenged what I know, because it questioned the security of the world. So there's something very different in the way we are and in the way we approach things. And I thought there was also something very different in the way we do popular science. Brian books are very rich of details, of information, very knowledgeable, very well-rounded and presented. I try to take away as much as, of course, Brian is also extremely good in taking away details, but his books are full of things. My books are try to take out as much as possible to say what we have understood with this or that. But then I read this book, the last book, Until the End of Time, and by Brian, and that here is doing something very different that he has done before. It's a very personal book. It's a very intense book in which he doesn't talk about physics only. He talks about the worldview that we can have as scientists. And he goes into the direction, he talks about values, he talks about beauty, he talks about what we are as human beings, he talks about free will, he talks about consciousness, he talks about religion, he talks about all these things. And the more I read it, and I was amazed by that, the more I found him so much close to myself. It's incredible how brotherly I felt by reading his writing, and it's incredible how he the entire set of things that touches him, interests him, fascinates him. The single problems he addresses in the book are exactly the same that I've been fascinating with, and I've been struggling with, and so much of where he goes, the positions he defends, the views he defends, because in this book he defends views, positions. I was reading and saying, yes, he's right. That's wonderful. That's a right way of thinking about all these deep problems, which to some extent are open, but to some extent we know and we have ways of bringing them together. And especially what he does in this book, which I think is marvelous, is he said in opening, Brian, you said in opening, well, have the big picture where we are inside, but it's more than that. We have culture is a large knowledge, is a large body of things in which physics is one piece, but all the aspects of knowledge are not in contradiction with one another, and that's what you're doing in a sense. You're showing that the ensemble of our thinking about ourselves, the world, from the physical world to what we call the spiritual world, to the cultural world, they can stay together. They can stay together in a way that doesn't deny one or the other, and the contradictions are apparent, provided that you have the courage of taking everything seriously in some sense. And I think this is wonderful. This is why I think this book by Brian it's so great. So I'm going to close by saying that I felt in this way when I was a kid in high school. I had a good friend. His name was Gianpaolo. We were friends as kids, and we were friends in high school. We were sitting together next one another. We still are friends. We were completely different. My mother would say he's the good copy and I'm the bad copy. When you draw you write your text for school, you first do a bad copy and then you put everything in good copy and you give it to professor. He was perfect. I was good at school, but he was unique. I mean, he had the best grades of Italy. He was absolutely he was perfect in everything. He was dressed very properly. He was saying things properly. He was clean. I was dirty. It was, and I loved him, and he loved me in this immense difference. He was, of course, had an immense intelligence. Now he's a medical doctor, super good in what he's doing. Went in another way. We had different political opinions. We have different views of the world, and yet I recognize him as not only a fantastic friend, but also as somebody who's with his intelligence I could react to. And this book by Brian remind me of my friendship with Gianpaolo. I think the image of Brian completely changed in my mind from this sort of a little bit cold distance, very good popularizer of genius, no doubt, very good scientist, but he believes in string theory. I don't. He believes in some way of multiworlds. I don't. He believes that things can be sure. That's not what I'm fascinated from this distance. Once he came down to tell us what he really think about the world, I find him that we're definitely in the same tribe, so to say, and our worldview is astonishingly similar. So it's a book, because we're talking about his book, which I strongly recommend to everybody. And in spite of the fact that I think he's wrong about string theory, he's wrong about a lot of things.
Well, that's great. It's great to hear, Carlo. And I should also say, congratulations on the great success that you've had with the books that you have written and rocketed to a new kind of fame in the literary world, which is fantastic. To bring these ideas out to the public in a way that's so rich and is able to move people significantly. So certainly congratulations on that front. And I do wonder, in describing the similarities and differences, I wonder if part of the differences emerge from the differences in the culture of, say, the string theory community versus, say, the loop quantum gravity community, if I just give those as broad names. I get the impression, and correct me if I'm wrong, because as you're saying, you and I, we don't know each other that well. We've crossed paths many times over the years, but it's always been relatively brief. But, there's a period of time when I was more in contact, say, with Lee Smolin as an example. And the impression that I got from those conversations is that the loop quantum gravity people, if he was representative of perhaps a generic way of thinking in that community, was willing to take in more philosophical ideas, was willing to kind of look at the meaning of space and the meaning of time, as opposed to taking them as a given and starting to calculate and build up a systematic approach to describing them in a quantum mechanical language. This is more in line with the string theoretic community. I mean, there are definitely many in the string and particle physics community where if the word philosophy comes into the conversation, eyes begin to roll, a sense of, not that kind of thing. We don't, whereas I don't get the feeling that that's the general zeitgeist of the loop quantum gravity community. Is that an accurate assessment in your experience?
Yes. Yes, completely. I think that the two words you're describing, perhaps a bit larger than just loops or just strings, but there is this. There are these two worlds. For instance, I don't know. Roger Penrose would fit in the loop category, even if you wouldn't call it a loop quantum gravity person. And in the string world, the I don't know, high energy physicists that might not be interested in strings, but are in that category as well. But yes, definitely, there is a culture in physics and fundamental physics, which has been developing for a few decades. Perhaps also for some good reasons, which is take away philosophy is just being confusing. And I think the split was after the war, when a lot of physics moved from Europe to the United States, and there was a distinctively American way of doing physics, trying to avoid the heaviness of the European way of doing physics, which was the one of Heisenberg, no doubt, and Einstein, no doubt. Einstein read Kant when he was 15. Was passionate of Schopenhauer. He read Hume. He read Mach. He was deeply philosophically thinking. And Heisenberg was under the influence of Mach, the same, and others. Schrödinger was reading the Upanishad and the Vedanta. So there was all this background of philosophy that in the Europeans of the early 19th century, when a big bunch of science after the war moved to America, there was a part of the community, and especially in the high energy community, that let me put it this way: quantum mechanics was working so well, and quantum field theory was working so well. It's just the good ideas were all there, the foundations were all there, so let's use it. And there was nobody would doubt that there was something not clear in quantum theory. We all agree, because we all disagree about how to think about quantum theory. But the priority was, let's use all that, right? And in parallel, there was another part of the community, of course, not only in Europe, also in America. I moved to Pittsburgh where Ted Newman was there, and he was a relativist, not certainly a loop quantum gravity person. So, in particular, in the relativity world, the idea that if you think about the philosophical questions first, you might go ahead, was dominant. And for quantum gravity, which is the part of the problem that loop quantum gravity and string theory overlap, because the two theories don't really address the same problem. Yeah. But there they really overlap. The attitude was so different. Somehow the string attitude was, well, let's look at the equations, and then maybe we'll find out what they say about space and time. And of course, if you talk with Lee Smolin, which is a good friend of mine, he would, and I would, think the other way around. Let's think carefully, what could it mean to do quantum space and quantum time, and that could allow us perhaps to find our way through the equations.
Maybe if I can, Carlo, provide some context for our listeners or viewers who are not necessarily familiar with the divide between string theory and loop quantum gravity. Let me just summarize the situation by saying that the two of you are on opposite camps of a scientific battle that is in progress, as your proponents and founders of two alternative ways of reconciling Einstein's theory of general relativity that explains the universe at the largest scale, so the macrocosm, with the quantum physics that provides a very precise, detailed description of the microcosm, the physics of elementary particles, and the physics of the smallest scales in the universe. So Brian Greene is a proponent and founder of the theory of strings, string theory. And Carlo Rovelli is a proponent and founder of loop quantum gravity. So please go ahead. I didn't want to interrupt. Just wanted to provide some context for the discussion for the viewers who are not necessarily familiar with that.
But both of us with ours, of course, with others, of course.
Of course, yeah, absolutely.
Obviously, right? Not certainly.
Yeah, with many others.
With many others, yeah.
Yeah, and it's an interesting thing though, because there was a period of time when Ashtekar and I, who's a major pioneer in the loop quantum gravity approach, we happened to be speaking at the same conferences. There was a stretch of time when we were just happened to be at the same conferences. And he commented to me that in all of our talks, we could have interchanged the first 15 minutes of what we were saying with each other in terms of when we're laying out the problems, laying out the issues, laying out the potential of a solution, what it would give us, and so forth. And then we would diverge when we got into the details of the approach that we were taking. But there is a resonance of the kinds of questions and the kinds of issues that we seek to resolve. But one quick way of summarizing the opposite camp perspective is that the string theorist tends to start with, say, the quantum mechanical particle physics mindset. And perhaps you would agree that the loop quantum gravity perspective tends to start with the general relativity, the space-time perspective. And so we try to meld the two together, starting from opposite ends. And the hope among some, and it really has not been realized as yet, and one question would be, are we closer to this vision or further from this vision than, say, a decade ago, is that maybe we'll meet in the middle. Maybe in some sense we're talking about similar ideas, or there are ingredients in each of the approaches that may be similar. And, maybe one of us is right, maybe the other is right. Probably neither of us is right. And we're just, heading towards some deeper synthesis of general relativity and quantum mechanics. But I think it's fair to say that neither camp can really claim victory yet.
Oh, that's for sure. I would definitely say that neither camp can claim victory, nor neither camp can feel defeat somehow.
Is there a sense of progress, though, in your respective fields? Do you feel that you're getting closer, or are we still far from getting a final answer to these fundamental questions?
I'm curious of Brian's views on that. Maybe then I want to go back to more general things, but I'm curious do you feel that string theory is in difficulty recently or not?
Well, obviously it all depends exactly what one means by the words difficulty and how one measures progress. And so if by difficulty, do we still have towering problems and mysteries that need to be resolved? Absolutely. If by difficulty one means that somehow the field has stagnated, then I would say absolutely not. I've been thrilled by the progress over the last 10, 15 years, especially in recent years, work that I would imagine that the loop quantum gravity community is at least interested to hear where it's going to go. This idea that we have these holographic descriptions, these alternative descriptions of a space-time environment in terms of a theory defined on a bounding surface surrounding that volume. And in that bounding surface, we don't have a gravitational theory getting rid of the deep conundrum of how to talk about gravity and quantum mechanics together. It's a purely quantum mechanical theory that, for instance, allows us to draw a link between quantum entanglement and the threads that stitch space-time together in the interior of that region. I consider these thrilling developments that, frankly, I didn't think that we would get to this point in my lifetime. I did think that we'd get to the point of perhaps making contact with experiment and observation. The fact that we haven't found supersymmetric particles at the Large Hadron Collider, the fact that astronomical signatures have not borne fruit. I would consider those things that when I was a student, by now I would hope that we were there. But as a student, would I know or think that we would have a non-perturbative and exact formulation of string theory in certain settings, and that we'd be able to draw these connections between qualities of quantum mechanics and qualities of space-time? I didn't think that we would get there. So on one side, I'm less happy, and another side, I'm more happy. So in terms of difficulty, on balance, I'd say it's incredibly positive.
Did you expect supersymmetry at LHC, or if you can try to think back, you were hopeful or very hopeful?
Right. Oh, I don't have to think far or hard on that one. I was extremely hopeful.
So that was a disappointment for you.
That's definitely a disappointment. Now look, it's not over. You don't
No.
know. I mean, the window is tighter and so forth. But if I look back over my career, the vast majority of the papers that I've written in one way, shape, or form involve supersymmetry. Sometimes, of course, just as a mathematical device to try to make progress in certain equations. But the underlying assumption was that the world is supersymmetric. And again, for those who perhaps don't know all of these ideas, the idea of supersymmetry is that the world has an additional symmetry beyond the ones that we've known about for a long time. You know, you can translate a system and the laws of physics don't change. You can rotate a system, the laws of physics don't change. There's a more exotic version of those transformations called supersymmetric transformations that we thought the world would obey. And if it did, there would be a whole collection of particles that we should find or could find at the Large Hadron Collider, but as yet we've not found. That could simply mean that the particles are much heavier than the most naive theories might have suggested, and therefore the Large Hadron Collider simply may not have enough energy to conjure those particles into existence. So the ideas could still be right, but if you ask me, am I disappointed? Yeah, absolutely, that we haven't found it.
So to connect with things that maybe people might have seen on today's newspapers, yesterday there was this announcement at Fermilab of this possible evidence of new physics. It comes from the measurement of the so-called magnetic moment of the muon, the infamous or famous, depending on whom you talk to, G-2 of the muon. So this is on the home pages of many media outlets around the world today. Are you excited? Does that say there are a couple of cracks that might that seem to appear in the standard model of particle physics? There's something that was also on many news outlets was since you talked about LHC, there was this LHCb measurement of lepton flavor.
Yeah, no, sure. I mean, look, we've been fond of saying for a long time that we are the victims of our own success at some level, because the standard model of particle physics, which has been in place in some sense for 30 years, and the Higgs boson, the last puzzle piece of the standard model, was confirmed back in 2012, almost 10 years ago. Because that theory works so well, we didn't have an opportunity to find qualities of the world that many of our more exotic theories were suggesting might be there. So any evidence that the standard model of particle physics may not be as complete a description of the fundamental particles of matter and the non-gravitational forces, any evidence to that is music to a physicist's ear, because it's an opening where perhaps we'll be able to finally go to the next level of understanding. Now, with G-2 for the muon, I think it's much too early to tell. That result is at roughly the 3 or 4, so to speak, sigma level of confidence, which for those who know that language suggests that, there's a 1 in a few thousand chance that it might be a statistical fluke. So it's not at the level where we can take it in and say, aha, this is definite, this is real, let's try to understand it. That doesn't stop people from trying to understand it. And people have suggested it might mean additional forces beyond the ones that we know about. We know about gravity, the electromagnetic force, the weak force, the strong force. Maybe there's another force, a fifth force. That would be absolutely thrilling. And that's exactly the kind of journey that we want to start to take baby steps along, that might lead us ultimately to string theory, some of the ideas of string theory. But of course, that journey is not baby steps away. That journey is many gargantuan steps away, but you get there by going beyond today's understanding. And maybe these insights from the experiments are suggesting that journey is about to begin.
Perfect. Okay, so maybe Carlo, we can.
Let me comment on that. Yeah. I of course I agree with the substance, everything Brian is saying about this news. If there's any difference, it's a difference of emphasis in. Let me make a couple of comments. One is that, as Brian is saying, we are suffering our own success. I mean, there's general relativity. which is 100 years old, and there's a standard model, which is, I would say also, maybe in the 70s. So it's half a century older. And if you think for a moment, the great scientific news of the last decades, those who have got to, Nobel Prizes, first page of the New York Times, with they're all been the discovery of the Higgs, the picture of the black hole, the discovery of the gravitational waves, the Nobel Prize, and including Nobel Prize given for old work, like the last one to Penrose and company. They're all not, we found something new, but all things, we've found that our theories are right, even where they were giving strange to believe predictions, like the existence of the Higgs particle. I mean, you have to make sense of things, you have to think there is another particle, and here it is, decades later, or black holes, which are still hard to digest by some even of my colleagues. So in a sense, we keep hearing that those theories are right. And quantum mechanics also. I mean, there have been spectacular confirmations of quantum mechanics, entanglement, hundreds of kilometers difference, which goes to the first page of the newspaper. But what we're really discovering is that what it was written in my textbook when I studied in the 70s is actually right. That's what we're discovering. Now, of course, as Brian says, there is something super exciting in that and something disappointing, because we would like to know more. And in the standard model by itself and generativity by itself, there's certainly missing things. We all convinced that there are missing things, and we'd like hints about that. And this could be a hint about that. So in a sense, it could be much more interesting, that the confirmation we got.
So maybe
however,
cosmology. Yeah, go ahead, Carlo. Sorry.
How we've been learning cosmology immensely. I mean, that's one thing. But cosmology seems to be remarkably coherent with generativity in Einstein 1917 version with the cosmological constant, and the standard model, plus perhaps an inflator who nobody knows about what it could be. Now, it's also true that the news is not the first time that we hear, we might be seeing some new physics in particle. It's like, crying wolf. We have heard crying wolf so many times. Maybe one day the wolf, it's actually there. Maybe this could be the way. I am cautious before jumping up and say, great. And I think everybody's cautious. I perhaps a bit more cautious. There are some the same day in which the news came out, there's a Nature paper with the lattice QCD calculations, because they play a role even in the magnetic moment of the muon, saying that it's not that the experimental results are far away from the 4 or 5 sigma, far away from the theoretical calculation, but the theoretical calculation, if you include non-perturbative, full non-perturbative standard model calculation, might be much closer to the result. So we don't know. It's open. It's certainly super exciting. In my heart, I hope that this is for real. But I also remember that it has been many people crying wolf in the past, and unfortunately, in a sense, for the moment, nature says, no, look, nature am working the way your textbooks say. Quantum gravity, which is what string theory tries to do and loop quantum gravity tries to do, it's a place where we are sure that the two theories don't tell us what is going on, right? If you we see things falling into black holes, we see them falling. We see the accretion disk, and then we see them disappear, and we have reliable belief that if you follow the actual matter following could cross the horizon and go in, and we have really no idea what happened next to that matter. It goes to, according to GR, it goes to R equals 0, where nothing clear. So quantum gravity is the open problem of understanding what happened there, what happened in the early universe. The way I view it is that string theory is very ambitious. It's sort of an attempt to overall picture, including all the other particles, all the other things. Loop quantum gravity is much less ambitious. It's just an attempt of describing the quantum properties of space-time. And loop quantum gravity is sort of a proof of existence. There is a Lorentzian four-dimensional quantum theory of space-time. We don't know if it's right because we don't have any direct empirical support, but there is one, and nature might be this way. We are all struggling to contradict it or to find confirmation. I find it's a beautiful situation in which it's not bad for science that there is things we know very well, an aspect of the world we know very well. We know that there is we know for sure that there is a lot we don't know. There are different hypotheses out there, and we're all struggling to make sense of them.
In terms of cosmology, so in your book, Brian, you talk about the future, the fate of the universe, and you consider this, of course, in the framework of our current understanding of cosmology. And so Carlo was mentioning that it is based on our understanding of general relativity, but of course you need to add these additional hypotheses, the existence of dark matter, the existence of dark energy, an inflaton field that it was responsible for the accelerated expansion of the universe at the Big Bang. How close do you think we are to a reliable cosmological model? And are you excited about the possible cracks in that cosmological model that seem to come from these Hubble tangent measurements, for example?
Sure. Again, any mismatch between theory and observation, and observation, it's those mismatches which historically have driven our understanding of physics. I mean, you can look at Einstein's special relativity as a mismatch between a Newtonian view of the world and the view of light that came out of Maxwell's insights. You can view the general theory of relativity as a mismatch between a Newtonian view of gravity and Einstein's own special relativistic understanding of space-time. So every step of the way, big insights have emerged from the mismatches, the tensions, the disparities. So yes, when we hear now that the expansion rate of the cosmos from the theoretical side and from the observational side are mismatching by an amount that may be believable and it may stand the test of time, well, yeah, that suggests that maybe we're going to have to go back to our theoretical understanding and tune it up in a way that it can match the observations. But I guess from 30,000 feet, putting the details to the side, I can't think that anybody wouldn't be enormously impressed and excited by the fact that we do have a mathematical description of the early universe, which is allowing us to understand, for instance, tiny temperature variations in the microwave background radiation, heat left over from the Big Bang. We can make calculations about how the temperature in space today, as we measure it today, should differ from one location to another. And those calculations agree with the observations to spectacular accuracy. You're talking about light, photons that have been traveling toward us since about 380,000 years after the beginning. They've been traveling over 13 billion years. And we measure these photons today, and the pattern of their temperatures agrees with calculations that we make about what the universe was like billions of years ago. That's mind-blowing. That is utterly, utterly spectacular. Now, does that mean that we have the full story? No, much as we were talking about with the standard model of particle physics. You have an idea, you have a theory, you test it, it comes through with flying colors, but you anticipate that as understanding deepens, you're going to be forced to go beyond it. And certainly with cosmology, seeing that we don't really understand the so-called singularity of the Big Bang, that's an issue that traditional cosmological ideas have yet to fully resolve or understand. So clearly, we're going to have to go further. And again, many people suspect that putting gravity and quantum mechanics together will be vital for understanding the singular nature of the mathematics in our description of the Big Bang, and whether that approach is string theory or loop quantum gravity or something else, nobody at this point can tell. But to me, it's remarkable that we can use our math to peer back to a fraction of a second after the beginning and make predictions that agree with observations. And it is also spectacular under modest assumptions that we can use our mathematical understanding to peer arbitrarily far into the future and make predictions for what things will be like. Now, will those predictions be borne out by what really happens in the far, far future? We don't know. Theories may change, our understanding may change. It's an act of hubris, in a sense, to make predictions over timescales that dwarf the timescales back to the Big Bang. However, based on what we know and what we've calculated and what we measured, we can do that. So we're so curious that we have to do it. Whether or not that literally is a picture of what the world will be like in the far future, who knows?
Gianfranco, you allow me to say one thing. If people listen to us and listen to Brian speaking, they might think that the book is all about that, about the physics and how nice and beautiful is our physics and cosmology, particles, and all that. But Brian's book is not about that. It contains a part of that. But the core of the book and many pages of the book are about for instance, values, about consciousness, about freedom, free will. I think that's the beauty of this book. It's just it's a vast attempt to articulate and to bring together, the perspective of a physicist who think in terms of particle fields, expanding universe, entropy, and all that, and asking question, how does this goes together with the fact that we see, we feel, and we have values, and we die, because that's a starting point, but it's also the ending point. Where is the source of what gives sense to? And it seems to me that, Brian, tell me if I'm wrong. You start by saying, well, when I was young, I got fascinated by mathematics. That was my first point, because it's eternal, it's perfect, it's never, which in some sense it is, of course. But at the end of your book, you end on a much deeper note, in my opinion, because the path you follow is that, look, you're saying, those who say that free will, it's an illusion, we should think without, are wrong. Free will in some sense it's right, but yet it's compatible with our physics. And those who say our values are an illusion, what we believe is beautiful, what we believe is it makes sense, it gives sense to our life, it's an illusion because the universe has no sense, are wrong, because of course the universe has no sense by itself. But there is a sense in which we are free, compatible, and there's a sense in which values are true because they come from us.
Yes.
And we have to find them in what we are. You emphasize the sort of high-level cultural aspect of that. I'm with you, but I also would say they also come from everything, from our biology, from our history, yep, from our culture, from our ideas, from the fact that they don't come from the outside, they come from the inside, does not make them false, make them real for us. Yep. I think this is a deep message of your book, and I think that's the core of your book. The reason I would like your book to be read.
Yeah, no, I thank you for emphasizing that point, and you're spot on target. There's a sense among some people that the only way that values and meaning and purpose can be real is if it somehow exists outside of ourselves, and we absorb it and imbibe it and live it. And that's why some are looking outward to the cosmos to find the source of those kinds of ideals, when the fact of the matter is a close look at how the world is put together, a close look at cosmology, a close look at the laws of physics, a close look at evolution and biology makes a very strong case that those qualities are not out there in the world. Those qualities, as you note, come from inside. We invent them, we manufacture them. And sometimes when people hear that language, they interpret it as kind of denigrating the things that matter to us most. And my view, and the point that I make in the book, is quite the opposite. The fact that we, collections of particles governed by the laws of physics, can come up with these ideas, that we can create things that fill us with a sense of beauty and wonder and awe. And the fact that we can have the sensation of beauty and wonder and awe makes it all the more spectacular, because it's coming from something where you wouldn't think that those kind of qualities would naturally follow from collections of particles governed by mindless, thoughtless, passionless equations. And yet we can have deep passion. We can experience that deep wonder. And to me, that makes it all the more spectacular that it's coming from us and not something that we're simply imbibing from the external world.
Yeah, that's what I like and love about your book, and that's why at the end I started with a lot of suspicion, and I ended up with by loving it. You see, we live in among the many cultural worlds in which we unfortunately immersed, or maybe fortunately. There is a split between. There is a apparent split between a denial of the scientific point of view, because according to some, forces us to not recognize other things that science cannot capture, on the one hand, and on the other hand, a vast scientific world that says no, those things are not in fundamental physics, therefore they're not real. And I find that both these positions are shallow, are very shallow, and they miss the point. And so I'm very much with you in and that's why I said that reading the book, I find that in spite of you wrongly believing that string theory is right and other things, and in spite of the difference of style that we have in so many things, which is good, which is we share this same, in a sense, deeper worldview, which is that no, there's no contradiction. There's definitely no contradiction. It's true that we have value. It's true that the values are valuable. It's true that we see beauty. It's true that we see justice. It's true that we can distinguish the good from the bad. And yet, we don't need to. We don't necessarily need at all to search the grounding of that outside the natural world, which happen to be regulated by laws that are described in science and physics. Things can be, and you have a way of saying that things can be described in different ways, at different levels, and the description of different levels are not in contradictions with one another. They can be one more powerful something and one less powerful some other thing. And of course, it would be foolish to, if I want to make my girlfriend happy, I shouldn't think about her as a bunch of protons and electrons interacting, because that doesn't help me. I mean, can't do. It's much more useful to use a completely different language. But this different language and different conceptual scheme is not at all in contradiction with me and her being a bunch of protons and electron interacting. This bringing together of different perspective, it's what surprised me in your book, which I didn't see before. Maybe you have been saying that over and over again. Maybe it has been your worldview since ever. But I think it's what science should, what popularization of science should do at its best. Popularizing science doesn't mean only, telling people, there's a standard model with 15 particles and they act on these 4 forces or 3 or 2 or whatever. And this is what we know, that's what we don't know. It's more than that. It's try to articulate what the current worldview says. The way is consistent with the rest, the way is not consistent with the rest, where the problems are, the things to be clarified, what we don't yet know, but believing that there is a coherence that is possible behind what we can say about the world. And ultimately, I find that I do find, like you, that this general view is reassuring also, I would say, ethically. It's also a way of, at the end of the day, being comfortable with the fact that we live in a world where there are no values that do not come from us, where our life is finite, and where there's the mortality you started from. My book of the Order of Time, the last chapter opens up by quoting an ancient Indian text in which there's the question, what is the greatest mystery of the world? And the answer is that the greatest mystery of the world is that everybody lives as they were immortal, in spite of the fact that everybody knows that we're all mortal. And I think we shouldn't live like if we were immortal. We can live happily knowing the limitation of our knowledge, the term of our life, our understanding, but in a way which is serene and is not challenged by what fundamental science tell us about reality.
Yeah, no, I fully agree. And I also, just to emphasize the point, would say that when one can take in the different levels of explanation, from all the way down at the physicist reductionist approach, all the way up to the insights of the philosopher and the artist or the theologian, when you put all of these descriptions of reality together, you just have a far richer sense of what the world is and what your place in that world can be. So all of these descriptions, all these narratives, all these stories provide different insights, and it's the collection of those insights that ultimately give us the fullest picture.
Yeah.
Fantastic. So I would gladly continue this conversation forever, but I know both of you have very busy schedules today. So thanks again. I remind our viewers that Brian Greene's book, Until the End of Time, is shortlisted for the Cosmos Prize for the best book in astronomy, physics, and mathematics. Thanks a lot, Brian, for joining us today.
My pleasure. Thank you.
Many thanks also to Carlo Rovelli, who acts as a jury member for the Cosmos Prize. Thanks a lot, Carlo.
Thank you, Gianfranco, and thank you, Brian, for this conversation.
And thank you, Carlo. Appreciate it.
And tomorrow we will have our final event with shortlisted author David Spiegelotte in conversation with Pier Giorgio Di Freddi. Thank you all for watching this video, and see you tomorrow.
Bye-bye.
Bye. Bye-bye.